Swayam Prabha. Digital India. Educated India.
We saw how to get three equations and three variables even when we have independent voltage sources in our circuit. The three variables are V1, V2 and V3, and I can solve for these three variables. Okay. Now this is fine. I took the equation for node 1 with an unknown current I12, and we took the equation for node 2 also has the same unknown current I12 but with opposite sign. We combined these two and eliminated that variable. Okay. What we would still like is a straightforward way of writing down all these equations without going through this intermediate extra variable. Okay. If you remember, that's what we did for nodal analysis also. We started out with Kirchhoff's law and then identifying each of the currents with the voltages across them and the resistances in those branches. But finally, when we wrote down the structure of the equations, we could simply look at the circuit and write out the conductance matrix. Okay, so that's what we want here also, and that's possible as well, because if you look at what's happening when we sum the equations for nodes 1 and 2, let me copy over this circuit. The equation for node 1, it says that on the left hand side we will have sum of currents leaving node 1 being equal to the independent current injected into node 1. And similarly, at node 2 we have sum of currents leaving node 2 being equal to independent current injected into node 2. When we sum these, what happens? We will have the sum of currents leaving nodes 1 and 2, that closed surface enclosing nodes 1 and 2, because in the first equation any current flowing between node 1 and node 2 will appear with a particular sign, and in the second equation the same current will appear with an opposite sign, with the opposite sign. Okay. So any current flowing between nodes 1 and 2 will get cancelled when you carry out the summation, and what is left is basically sum of currents leaving the surface enclosing nodes 1 and 2. Okay, basically this surface. This is the surface we are talking about here. And what will we have on the right hand side? We will have the total of independent currents injected into nodes 1 and 2. Okay. So that's all that's there to it. Instead of looking at a single node, you look at the surface enclosing the two nodes. Okay, and such a surface enclosing multiple nodes is known as a super node. Okay, so the bottom line is that if a voltage source is connected between two particular nodes, you form a super node with those two nodes and write the equations for the super node. You take the sum of all currents leaving the super node and equate that to the total current being injected into the super node. Okay. How do you do this? You still have the same variables V1, V2. Okay, we have the supernode. The supernode consists of multiple nodes, each with its own voltage. Okay, so the point is you don't have to worry about the currents going from node 1 to node 2. So you still have these terms corresponding to V1 and V2. So V1 will get multiplied by sum of conductances at node 1, and V2 will also get multiplied by the sum of conductances at node 2, and there will be all the other terms. Okay, if you have conductances between node 1 and some other node, you will have other terms corresponding to that. Okay, so this will be obvious from the example. This is the supernode. So the combined equation for nodes 1 and 2 is nothing but the sum of currents leaving the supernode through resistors, which corresponds to V1 times G11, because at node 1 we have only a single conductance, but at node 2 we have these two conductances G22 and G23. So we have V2 times G22 plus G23, and you can have conductances going from any one of these nodes to other nodes outside the supernode, and those will appear with a negative sign as usual, minus V3 times G23. Okay, and if we happen to have some other node with V4 and G14, we would also get minus V4 times G14 and so on. This is not in our circuit right now, but if it was there, that would also appear. Okay, we have to look at total current from independent sources being injected into the supernode. So we have I1 going into the supernode and nothing connected here. So the sum simply equals I1. Okay, so this is not there. I just took that as an example. So this equation, which combines the equations for nodes 1 and 2, can also be written down by inspection. What you have to do is make a supernode that combines the nodes between which the voltage source is connected, and on the left hand side you write all the currents leaving the supernode through resistors. On the right hand side you have all of the independent sources injecting currents into the supernode. Of course, you always use appropriate polarities. Okay, so that's how you can write this by inspection. And of course, the voltage source equation can be easily written down by inspection. So V1 minus V2 equals V0. And for node 3, the same thing that we always used applies. We'll have V3 times sum of conductances, which is G23 plus G33, minus V2 times G23. Okay, and the whole thing will be equal to I3. So we have our three equations and three variables, and we can solve for the node voltages. Okay, these equations can also be put into matrix form, but the matrix form will not have any symmetric structure like it did earlier. Okay, in fact, the matrix form, I'll continue to call it conductance matrix, but not all elements will have dimensions of conductance. Okay, let me show it for this example. So let's say the first row, I write it for the supernode, okay, which will consist of G11, G22 plus G23 minus G23, V1, V2, V3, and this will be equal to I1. And the second equation is for the voltage source. It says that V1 minus V2. Remember, this is matrix multiplication. This number multiplies that, this one multiplies that. V1 minus V2 equals V0, the voltage of the voltage source. And finally, we have the equation for node 3, which says that G33 plus G23 and minus G23 will be equal to I3. Okay. So this is the G matrix. I will continue to call it conductance matrix, but these are not conductances. Okay, they are dimensionless quantities. And similarly, the right hand side here is the source vector. So it consists of all independent sources. Okay, so that way this structure is still nice. We have some matrix times the unknown vector to be equal to the source vector. I still denote it by I, but this source vector now also has voltage sources. So the source vector will have both independent voltage sources and current sources. Okay, this is fine. So when you have voltage sources in the circuit, you can form supernodes consisting of the nodes between which the voltage source is connected, and then go ahead with nodal analysis. Okay. So in summary, when you have voltage sources in the circuit, you form a supernode consisting of nodes to which the voltage source is connected. Write a single equation for the supernode, and you add the constraint imposed by the voltage source between particular nodes. Okay. Now let's take a couple of other examples of having voltage sources in different ways than I showed. So let's say the circuit is like this. That is, there are two voltage sources and they have a common node. Okay. For instance, here this voltage source is connected between node 1 and node 2, and another one is connected between node 2 and node 3. So what you do in this case? Clearly, you have to make a supernode of all these three nodes, because you don't know the current through this voltage source or that one, and those have to be eliminated from our equations. So you form a single supernode out of three nodes. In general, it could have multiple nodes, because if you have voltage sources connected in such a way between nodes, then you have to form a supernode with more than two nodes, and that's okay. So you still write KCL equations for the entire supernode. On the left hand side, you will have currents through resistors coming out of the supernode, and on the right hand side, you will have the total current injected into the supernode, I1 plus I3. And then you have two more equations. So if this is V1, V2 and V3, you know that V1 minus V2 is V0 and V2 minus V3 is Vx. Okay. So if you combine more than two nodes, if you combine three nodes into a supernode, you will lose two equations. But of course, you will have two constraints from voltage sources, and that will take care of it. Okay. Another possibility is in a circuit like this, where a voltage source is connected between a particular node and the reference node. Okay, if you see V0 here, this is the reference node. It's connected between this and the reference node. Okay. So what do you do in this case? Now you simply do not write the equation for node 1. Another way to think about it is that you still form a supernode, and this supernode consists of node 1 and the reference node. And you are not going to write an equation for the reference node anyway, so you don't write an equation for this supernode. And the voltage source constraint directly gives you this node voltage. It tells you that the voltage source constraint tells you that V1 equals V0. Okay. So essentially this node voltage is already given to you. It is equal to V0 and you don't have to solve for it. Okay. So you don't write the equation for node 1 and you just write equations for nodes 2 and 3. Okay. So that's all that's there to it. Clearly in this case, when you have a voltage source like this, the voltage at node 1 will be equal to V0. Okay. So you don't need to solve for this one. You can take it as a given and solve for the rest of it. Okay. Or if you still want to write 3 equations in 3 variables, you would have written it for V2 and V3 and you have this equation V1 equals V0. Either way is perfectly fine. Okay.